Да. Так. Марк, вы посмотрели в прошлый раз?
Нет.
Окей.
Да, надеюсь, я все. Ну, я надеюсь, я
Хорошо. Нет, нет. Ладно. Okay. So I think we'll continue in English, and точно? Аник не расстроится? Хорошо, ладно, да, давайте по-русски. Значит, что мы хотим сделать? В прошлый раз у нас мы начали разговор про кольца Кокса, мы кое-что сформулировали, но мы ничего особого глубокого не успели доказать. Вот сегодня я бы хотела что-нибудь доказать, но для того, чтобы доказать, нам что-то потребуется знать про факторы. То есть мы уже немножко говорили про факторы, но как-то еще раз скажу, и опять ничего не докажу. Что нам здесь нужно будет сегодня? Нам сегодня нужно будет, во-первых, когда у нас первый случай, если у нас наше многообразие X афинно, и группа G действует на X, то у нас всегда можно рассмотреть алгебру инвариантов C, X, G. Вот. Это будет конечно порожденная алгебра без нильпотентов, и поэтому, значит...
Здесь не нужно требовать, что там G будет.
О, точно, да, вы правильно сказали. Да, то есть если, давайте так скажу, если C, X, G конечно порождена как алгебра, то у нас есть, очевидно, нет нильпотентов, то мы можем рассмотреть ее спектр. Это будет афинное алгебраическое многообразие, и весьма логично назвать его фактором X по действию G.
Как множество они будут совпадать?
Это хороший вопрос. Значит, я не хочу разбирать сразу все примеры. Самый, наверное, пример, который устно можно разобрать, когда у нас есть действие гомотетиями. C со звездой действует, я не знаю, там на каком-нибудь пространстве афинном. Тогда инвариантные функции только константы. И поэтому как бы вот эта штука, это будет точка. Ну, пока ничего хорошего не получилось. Да, значит, сейчас я все напишу. Я сейчас написала, что можно рассмотреть вот такую штуку, когда CXG конечно порождена. Дальше давайте напишем про редуктивные группы. Значит, если группа G редуктивна, не хочу все писать, но вот G редуктивна, то есть какие группы редуктивны? Тор редуктивен, конечные группы редуктивны. То есть, как бы, например, G конечно или G тор или квазитор. Значит, тор на конечную. И еще что подойдет? Ну, пока хватит. Если G редуктивна, тогда CXG всегда конечно порождена. Значит, CXG конечно порождена.
Зачем нам сейчас конечно порожденность этой вещи?
Ну, мы же хотим спектр брать. Мы хотим получить какое-то афинное алгебраическое многообразие.
Ну, да, чтобы многообразие было.
Давайте то, что не подходит. Давайте я вот здесь напишу для конца пример. Да, вообще, что такое редуктивная группа? Группа редуктивная, ну это тоже отдельная теорема, когда все ее представления вполне приводимы. Вот, пример нередуктивной группы. это вот C плюс действие. Когда у нас есть 1, А0, 1, А лежит в C. Однопараметрическая группа изоморфная C+, и у нее есть представление двумерное, ну вот мы действуем на двумерном пространстве, в котором инвариантное подпространство не выделяется прямым слагаемым. Вот. То есть про редуктивные группы есть разные варианты их определить. Теоремы, которые доказывают, что все это одно и то же. То есть одна из теорем, что любое представление вполне приводимо, раскладывается в прямую сумму неприводимых. Да. Any representation, any finite dimensional representation is a direct sum of irreducible representation. This can be taken as a definition of a reductive group. Of course. So for G finite, it can be proved via taking the Bekar that any representation is a direct sum of irreducible representations. There is a direct procedure to write what is the second summand. So any finite group is reductive. For me, I don't want to talk much about reductive groups, but I just use that everything which is true for reductive groups works well for finite groups and for quasi-Toric. So I will use it. Okay. Дальше. Is it okay in Russian? Хорошо. Значит, дальше, что такое, вот как мы сейчас показали с гомотетиями на пространстве, само по себе понятие категорного фактора еще ничего не гарантирует. То есть вот здесь мы можем сказать, что вот это называется категорным фактором для действия группы G на многообразии X. Вот, что мы хотим потребовать, то есть мы хотим, чтобы, если у нас есть два замкнутых G-инвариантных множества, то чтобы их проекции были в образе тоже не пересекающимися. Пам-пам-пам. Ну или давайте, может, не будем это все. Что нам точно нужно? Ладно, давайте сформулируем. Значит, хороший категорный фактор это такой, что, во-первых, для открытого, ну что получается, у нас есть x, получается, пускай это у нас y, и у нас есть отображение из x в y. Ну, поскольку, значит так, пускай это пока афинное все. X афинно. У нас есть обратное отображение на функциях. Мы можем вложить вот это вот zxg в zx. И поэтому у нас есть вот такое вот отображение. Вот. Мы хотим, чтобы для у открытого в y хотим, чтобы у нас алгебра функций на u совпадала с инвариантными функциями на прообразе этого множества в x. Мы хотим потребовать вот это вот. Дальше мы хотим потребовать, чтобы если есть множество в x, подмножество замкнутое и g-инвариантное, То есть если оно G-инвариантное, вот оно здесь куда-то проектируется.
G где действует вообще?
G действует на X. G действует на X, а Y это определяется как спектр CXG. Это фактор. Пока что давайте предполагать, что группа G редуктивна. Вот, значит, мы хотим, чтобы замкнутое и G-инвариантное множество переходило в замкнутое подмножество в Y. P от W замкнутое в Y. И еще мы хотим, чтобы, если у нас есть два подмножества, не пересекающиеся, замкнутые G инвариантные в X, чтобы их проекции не пересекались в Y. Вот. Но на самом деле есть теорема, которая говорит, что для редуктивных групп все хорошо. То есть для редуктивной группы у нас всегда получается, что всегда категорный фактор является хорошим, и, например, каждый слой содержит ровно одну замкнутую орбиту. Вот. Но с категорным фактором бывает по-разному, бывают разные орбиты. А самое лучшее, что может быть, это когда слои являются орбитами. Вот. Значит, самое лучшее, что вообще бывает, это геометрический фактор. Геометрический фактор – это когда слои – это орбиты. Вот. Значит, да, например, это выполняется, если все орбиты замкнуты. Опять же, я сказала, не написала, что для категорного фактора и редуктивной группы G в каждом слое есть ровно одна замкнутая орбита. Но получается, что если все орбиты замкнуты, то каждый слой является одной орбитой. Правильно? Да. Вот. Хорошо. Еще что нам надо, прежде чем мы вернемся к коксам Кокса. Вот, я забыла сказать еще одну вещь. Значит, хороший категорный фактор. Когда у нас не афинное многообразие X, мы можем сказать, что значит, хороший категорный фактор, если X не афинный, если есть покрытие X афинными множествами, для каждого, значит, пускай X это объединение каких-то W альфа открытых афинных. И если у нас есть Y такой, что покрыт какими-то чего? Sorry. Okay. Just what was in the beginning of the lecture I just gave a brief sketch of what quotients of algebraic group actions do we have. So categorical quotient, which can be bad. This is categorical quotient. G is reductive today. So I say that it is always defined for G reductive, but sometimes it has no sense. So to be of practical use, we say what is a good categorical quotient. It means that generally if we have a closed subsets, then if we have disjoint closed subsets, then the images are also disjoint. Yes, and I say that for quotients of reductive groups, each fiber contains exactly one closed orbit. And I say that the property to be a good categorical quotient can be checked locally. You cover X by fine open subsets and you cover Y. If for each alpha...
Are these unions finite?
Sorry?
This union is finite.
Yes, finite. Cover. So if for each alpha we have that U alpha is it is denoted by double slash, is a good categorical quotient, then all in total it is called a good categorical quotient. So all the properties are held, all this stuff remains valid. If we have two closed disjoint sets, then their projections are also disjoint. And one more thing to add, almost geometric quotient is when we replace our variety by an open subset on which the quotient will be geometric. So X is our variety. We take some open U, open and G invariant, such that U over G is a geometric quotient. So I say about notation. If we have a geometric quotient where fibers are orbits, then it is natural that we write X over G, because it is indeed the orbits. And in the case of categorical quotient, we use double slash because there is a fiber which contains one closed orbit. There is no bijection between orbits and fibers. Okay.
So in the case of scalar motion of Cn by C star, we can also geometric quotient, right?
Yes. Cn over C star, the diagonal action. Yes, if we take Cn without 0 over C star, it is our favorite example, which is P1, Pn minus 1. It is the geometric, now it is the geometric quotient.
C star is reductive.
Yes. Yes, it was somewhere in the sheet. If the torus section is diagonalizable, then there is the direct sum decomposition. Every one-dimensional subspace is its irreducible representation. Okay. I think we discussed all the general facts, and now we can pass to our situation of Cox rings. So, first of all, I think we will try to prove the theorem. First of all, I formulate one easy statement. We discussed it last time, but we didn't finish the proof. And then we will discuss the more difficult theorem. So what did we have? Sigma is our fan. X sigma is our toric variety. Then we have variables x rho. For each sigma, okay, let rho the set be all the rays of our fan. And for each ray we have a variable x rho. So we see it in the polynomial algebra. It has as many generators as we have the rays of the fan. And for each sigma maximal cone in sigma, we have the monomial x sigma check is the product of all rho which are not in sigma 1 x rho. This is a monomial. Now we have this set, this zero set of the ideal generated by all these monomials. Z of sigma is the zero set of the ideal x sigma hat. Sigma, you can write maximal cone, you can write cone, it doesn't matter. So it was our zero set. In our main example, the projective space, this zero set was the origin. If you didn't understand the last lecture, you just think that Z sigma is just the origin. Okay. What is our aim? Our most general aim is that we take C power sigma of 1, as many coordinates as we have raised, we throw out Z sigma. Then we want to take a quotient over some reductive group G, and we want to get our initial variety. And for this, we have an explicit construction. What is the explicit construction? We have, first of all, we want to construct the new fan, which is called the sigma tilde.
So Z of sigma is not in our, where is it?
It is here. You see, we have as many variables as we have rays. For each ray, we have a new variable. So now we see it in the polynomial ring of these variables, the polynomial ring is the algebra functions on the complex space of this dimension. And so we have some monomials. I can recall our basic example. This is P2. We have three variables x1, x2, x0. Each x sigma hat is x0. Then we have x1 and x2. The zero set of this ideal is when this equals 0, and this equals 0. So,
Yeah, okay, that makes sense.
But we're going to construct a new fan, and you have to follow. What is a new fan? We have, it will be in this space, in the space of dimension sigma of 1, just formally. Basis is E row labeled by our sigma 1. But now these are new linearly independent vectors. Just new vectors, but labeled by our arrays. And we have that the new fan contains sigma tilde, a cone in sigma tilde, if and only if the corresponding, so I say that we have a projection C power sigma 1 maps to n when E row maps to U row, the primitive vector on the edge. C sigma tilde is a cone in our new fan if and only if sigma, so E row 1, etc. E row s. If and only if U row 1, U row s are a cone in our fan sigma. Just formally. If several vectors form a cone in our fan, then we say that their preimages will form a fan upstairs. Why is it a fan? The intersection of two cones should be also a cone.
So, what is it, this morphism? It's morphism of what? Here, where we
Yes,
see
yes.
the power of sigma 1.
We just say that our new fan will be more or less the fan of this toric variety. So some basis
Of what variety? X
of this complex space.
just complex space.
Just complex space. So just linearly independent new basis vectors. Just they're labeled by rays.
Yeah.
If they map to U row are labeled by the edges of our fan. Just if we, again, our projective space, these are three vectors. For the projective space, their sum is 0. For the new fan, these are just three linearly independent vectors. And we say that we have a cone upstairs if the corresponding U row form a cone here. So we take everything but the cone generated by three vectors. Because all the three vectors in total do not form a cone for P2. But all the other subsets, they do.
Yeah. Okay.
So this is the construction of a fan sigma tilde. And we wanted to prove something. First of all, the first part is that this is a toric variety with this fan. First that we want to prove is that C sigma 1 without the sigma is the toric variety of the fan sigma tilde. Okay. The second part that we want to prove is that we have a morphism of toric varieties. The second part is that this map so E row to E row defines a map of the corresponding toric varieties. And the third part is that the resultant toric morphism so this is pi from C sigma 1 without the zero set is mapped to our toric variety, is constant on G orbits, so where I define G, we have an exact sequence. 1 maps to G, maps to C star power sigma of 1, maps to the torus Tn, maps to 1. So this is just the quotient of this very big torus by Tn. Tn is the torus corresponding to X sigma, the torus of X sigma, and this huge torus is the torus of the affine space. Okay. Okay. Let us discuss the proof of this statement. First of all, what is why is this a toric variety? What do we throw out? I think I need to define it. What is a primitive set? Primitive is a subset in the rays, a subset in sigma 1, which is not in sigma for all sigma, but every its proper subset is. So a subset in the rays such that it looks in all the directions and minimal with this property. What do we want to say? First of all, we want to explain that Z sigma is the union of coordinate hyperplanes labeled by primitive sets. And what else? So clearly, the fan upstairs is a sub-fan of the fan of C sigma of 1. Okay? Is it clear? At the moment we have two fans. For the proof I need the third one, which is a very silly fan. Just I'd say sigma bar is the fan of all subsets in a row. So in fact, fan of the complex space. Okay? My statement is that Z sigma is a union of some coordinate hyperplanes. So if we throw out some coordinate hyperplanes from sigma bar, no, from C power sigma of 1, it will remain toric. It will remain T-invariant with respect to the big torus, which with the coordinate action. And the only thing to check is that the fan which will be here, it will be exactly the fan that we constructed here. So, more precisely, I say that Z sigma is the union of we take C a primitive subset x row 1 equals x row 2 equals of such subsets. Okay, this is a coordinate hyperplane. Why is it so? What is Z sigma? What is the ideal? For each cone, we take all the variables which do not enter in it. So, why is it exactly the same? Why every such subset is in the zero set of our ideal? It is just because if we take each equation, it will contain at least one variable of our primitive set. All the elements of the primitive set cannot belong to any cone sigma. So the one coordinate which didn't come in sigma, it will vanish the monomial x sigma hat. So each hyperplane of this form is indeed in Z sigma. And vice versa, if some coordinate hyperplane belongs to Z sigma, we can take a maximal by inclusion, we can take a minimal with respect to inclusion hyperplane, and clearly its coordinates will form a primitive set. So, indeed, Z sigma is the union of a primitive, of coordinate hyperplanes via all primitive subsets. Okay, and now what about our fan? In our fan, we don't have cones corresponding to primitive sets, so we throw them out. So here all the cones that we have, they have edges which are in some cone. So we don't have cones corresponding to primitive sets. So we are done. We have the orbit cone correspondence for the toric variety C power sigma of 1. And the orbit cone correspondence says that some H orbit is, we say what coordinates are 0 and what are non-zero. And if we throw out subsets where something vanishes, we can take the one of the biggest dimension of the smallest number of zeros, take its closure, and that will be what we throw out. So for each primitive subset, this is a toric subvariety, which is a closure of the corresponding orbit, where all the remaining variables are non-zero. And we are done. We explained that sigma tilde is the fan of sigma tilde, the fan of C power sigma 1 without the zero set of our ideal. Any questions? This was last time, but I explained it more in detail.
It's okay.
Okay. What next? The map defines the map of the corresponding toric varieties. This is obvious, because we said that the map of fans, so first of all we have the map of lattices. The lattice Z power sigma of 1 is mapped to the lattice n. Each basis vector is mapped to some vector in n. And now each cone is sent to a cone. So this map is compatible with fans. So it defines the map of corresponding toric varieties. And now what about our group G? Why is it constant on G orbits? We should say that, in fact, this torus, it is a subset in this set. So the set of points for which all the coordinates are non-zero. And we can write that if we take G from C star power sigma of 1 and X from our variety C. Then the projection pi, it is equivariant, so pi of G applied to X is pi of J pi of X. since we have the toric map, our map respects the fans, so it is T equivariant, and we can write this. But now, since G is in fact in the kernel here, we can say that this is in fact pi of x. So G can be viewed as a subgroup of this G from G. It can be viewed as an element of this big torus, but which maps to 1 when we go to the torus Tn. So this is 1, and this is exactly pi x. So on the G orbit, pi maps any 2 points of the G orbit to 1 point. So in some sense, if we understand that G is reductive, we can think of it as a quotient of a G. So what is G? If we know about the Smith normal form, we understand that G is a product of some torus and of some abelian, of some finite abelian group. It is when we have the map of lattices, we take the home to C star.
G is finite?
No. G is a product of some torus and some finite part. In some cases, it is just a torus. Then everything works better. Okay. Now I will formulate the theorem. I'm not sure that we'll prove it completely today. And it is a more or less recent result. It was done in 95th or like this. And did you notice that I mentioned a new source, the article of Cox? Not only the book of Cox, but also the article where, in fact, Cox rings appeared. And in that article, in its first version, there was a mistake. So there was a very nice statement about how G acts on the Cox ring, but the statement was more or less true, but the proof was wrong. And all in total, these are results of Cox and also, I don't know how to say, they proved the theorem which I write now. So theorem, let X sigma be a toric variety without toric factors. So sigma of complete dimension. It can be done for varieties with torus factors, but it is technical and not very difficult. And now we consider the pi which we have today. Pi is from C power sigma of 1 without the zero set, which maps to our toric variety. X sigma. Then the following is true. First, pi is an almost geometric quotient. Pi is an almost geometric. For the action of G is defined here, for the action of G on C sigma of 1 without the zero set. In particular, we can write that X sigma is the categorical quotient over G. The second is much more complicated, is that pi is a geometric quotient pi is a geometric quotient if and only if sigma is simplicial. So the proof of this statement is not direct, it is not consecutive. So first of all, we are going to show that we have a good categorical quotient. Then we are going to show that for a simplicial fan, it is indeed a geometric quotient. And then we can say that if we have some fan sigma tilde, there is a sub-fan which is simplicial. For any fan sigma tilde, we can take at least its skeleton, at least its rays, and they will give us a simplicial sub-fan. But a simplicial sub-fan gives us a torus invariant open subset. And if we show that for simplicial fans pi is a geometric quotient, then all in total we have an almost geometric quotient. So this is our plan, like this. Let us try to prove all this stuff. So first of all, about almost geometric quotients. No, about good categorical quotients. What is the pre-image of U sigma? Of an U sigma is just an open T invariant affine subset in our X sigma. In fact, it is some T invariant subset upstairs, but we know that the projection of some cone tau tilde in sigma tilde is in sigma if and only if tau is a face of sigma. So if something has mapped to U sigma, it was tau tilde for tau a face of sigma, nothing else. Okay? So in fact it is the open subset U sigma tilde upstairs. So sigma tilde is a cone of the same dimension as the sigma, but the dimensions are different. U sigma tilde is of a bigger dimension than U sigma. Okay, so let us denote by sigma the toric morphism which sends U sigma tilde to U sigma. If we show that it is a good categorical quotient for each sigma, then by some lemma, with the open covering, we say that all in total pi will be a good categorical quotient. If we check that, if we check locally that pi is a good categorical quotient. Okay. For the next 10 or 20 minutes, we're going to discuss pi sigma. What is pi sigma? So, what is pi sigma on coordinate rings? There are algebras of functions C U sigma. We know what is this. These are monomials for the cone sigma dual in M. Do you recall? In the very beginning we had that this is the monomials which belong to lattice M intersected with sigma check. And on the other hand, we have the G invariance C U sigma tilde G invariant. So what can we say about pi sigma dual? First of all, what is the algebra of regular functions on U sigma check? There are some coordinates which should be positive and some which can be arbitrary integer. So sigma tilde in fact gives the semigroup it is sigma tilde check intersected with the lattice is the set of collections A row such that A row are non-negative for all rays of sigma. Okay? It was our construction of the cone sigma tilde upstairs. So U sigma tilde, so the function C is the monomials A x row power A row, where A row are non-negative for the rays of sigma. which is in fact the localization of our Cox ring by sigma hat. We just said that for Mark, this is in our polynomial algebra, we took the subalgebra generated by all these monomials. So if we localize, it is what we need. So the ones which can be in negative powers, these are the ones which are not in sigma. Okay. What next? What next? We have the map. First of all, we have the map Z sigma 1 maps to N, and we have its dual map M to another copy of Z sigma 1. How does it work? Where do we send a monomial? So this is pi sigma star, and the pi sigma star of chi m, it just goes to the variable x row will be in power m u row. Okay, this is our map by sigma star. Indeed, if we took m from sigma check, then all mu row will be non-negative for raise of sigma. For this given sigma, these values will be positive. It agrees with this, and all the other variables will enter in some integer, but maybe negative power. And now we can say that pi sigma star, it maps C sigma check intersected with M to the localization as x sigma hat, and also we know that pi is constant. Pi sigma is constant on G orbits, so we can say that it maps to C x hat G invariant, which lies in S x sigma hat. Okay, since pi is constant on G orbits, we proved it in the previous lemma. Then it maps to the G invariance here. Now let us and also we know that the image of pi sigma is dense in U sigma because it contains the torus. And so, from this we obtain that from the density of the image, we conclude that pi sigma star is injective. This is the basic fact. If the map if we have a map of two algebraic varieties such that the image is dense, then the map on the algebra of regular functions is injective. If it had a kernel, then the map would be to some closed subset which cannot be dense. Wonderful. We want to show for this map, we know that it is injective, and we want to show that it is isomorphism. So now we want to prove surjectivity. We prove surjectivity by hand. Just we take any polynomial and look at it attentively. How are we going to prove surjectivity? Suppose that we have f which belongs to this localization. F belongs to S x sigma hat. It can be written as the sum of monomials. So let f be equal to the sum of CA x power A. So A is a multi-index. A is a product of some variables x row power A row. And we know that for each row from sigma 1, A row is non-negative. Okay? How does G act on F? When is F G invariant? So we take T in J. T is a multi-index. T is also a multi-index, and we can treat G as a subgroup in the big torus, C star power sigma of 1. What is the action? It will be T applied to F will be the sum of CA T power A XA. So it comes out. So the multi-index T powered by the values of A row. But we said that F is G invariant. What does it mean? It means that if CA is not zero, then what sorts out this T A should be equal to 1. But what does it mean it is equal to 1? It means that in fact it is we had an exact sequence 1, then G, then this big torus sigma of 1, then our torus Tn, and then 1. If T power A equals 1, it means that T, in fact, is given by some monomial M. So a row should be equal to M U row for each row from the big fan. Also, last time we had an exact sequence which described what is G. How can we write equations for G given here? So we need that all a row should be of this form, and also we know that XA was in the localization. XA is in sigma hat. So for all rays of sigma, it should be M U row non-negative. What does it mean? It means that M which is here, M which is found here, is in sigma check, because M is in sigma check. Okay, and it means that this polynomial is in the image of pi sigma star. Of pi sigma star. And we proved the surjectivity of this map.
Can you please repeat why a row is of this form?
I can explain, but I need to find the formula. So last time we described this map. So when so G is the kernel of this map. So there are such strings of non-zero elements which map to 0 here. What does it mean? We wanted to write the dual maps and say that if something goes to 1 here, then for the dual map, so one moment, there was equations for G. Yes. So we said that G is the set of T row such that the product T row power M U row equals 1 for all M in M. We had this lemma, and we said that M to Z sigma of 1, it was defined by M maps to m euro, and so if it goes to 1, all these should be 0. Okay?
Can you please?
Yes.
Okay, yes.
Okay. So we have explained everything about pi sigma star. We have explained that pi sigma star is isomorphism. So indeed, on one affine chart we have a good a good categorical quotient. Okay, and all in total, it is a good pi is a good categorical quotient. Okay. Now we have something more complicated. We want to show that we have a geometric quotient if and only if it is simplicial. I need to erase something. I think I erased this. So now, so locally we show that pi sigma is a geometric quotient. If and only if sigma simplicial. For this, I think we will need one statement which I am not going to prove right now, but we can make it during the seminar. So it is not very complicated. But it deals with non-normal toric varieties. By non-normal toric variety, let us it will be the variety with the density orbit. Variety with the t action and dense t orbit. If you remember, we've had such examples at the very beginning. If we take some set of characters, we don't check that it is saturated and we take its orbit closure. The set XA for non-saturated A. So why do we need this? Suppose that we have a point P in X, and we have another point in the torus Q in T, where T is a subset of X. So we can always take an orbit of Q such that its closure contains P. So there exists one parameter subgroup in the torus such that P is the limit of lambda T applied to Q. It can be done easily using relative interiors for the usual normal toric varieties, and it needs some technical skills to show the same in the non-normal case. But I think it should be obvious to you in the normal case. Just P is in the orbit corresponding to some phase. Then we take a point in the relative interior. We take the corresponding one parameter subgroup, and it sends the interior point to P, more or less like this. So we will use this lemma without proof, and now we want to prove in one direction, is that from simplicity we will show that the quotient is geometric. The quotient is geometric. It means that all the orbits are closed. So we want to show that for every point its orbit will be closed. We take a point P in U sigma tilde. It can have some stabilizer. So we want to take G orbit of P, and it will be toric with the torus isomorphic to the identity component of G, quotiented by the identity component of the stabilizer. So we know that G is a direct product of some torus and some abelian group, and some finite abelian group. So G0 stands for the torus, and then it can happen that there is some stabilizer. The stabilizer will itself be a torus as a subgroup of a torus. No, it will have a connected component, a torus. Okay, and we say that the G orbit of P, its connected component will be T applied to P, the connected component of G applied to P. So what is we want to prove that in the case of simplicial sigma, we want to prove that the G orbit of any point is closed. We are going to write it down directly. We say that TP is a toric variety which can be non-normal because it is just we applied the torus to our point P and we took the closure. It contains a density orbit and now it is a subvariety. Okay, so by this lemma there is a point of the torus, there is lambda from C star to our torus and some point Q in P such that P can be written as the limit lambda T applied to Q. Now we can take the preimages of everything in our group G and now we say that G0 is in C star power sigma of 1. Okay? Because G0 is just the identity component of our group G. So we can lift our subgroup lambda from T to G0 and we can find a representative for Q in G0. So lambda, we can take lambda from C star to G0. So lambda of T, it is some abusive notation, but I don't want to add bars because I will forget them. We will have that lambda is the multi-index T power a row for some integers a row. Now, but also we know that lambda is a subgroup of G, so it is given by the conditions and so the sum of a row U row equals 0, okay, as we did last time. And now we can write precisely what is the limit here in coordinates. Let point P have coordinates P row and Q have coordinates Q row. Then we have P row is the limit when t tends to 0 of t power a row q row times p row. It is just, we wrote this in coordinates, and we know that for the rays of our cone sigma, everything is in the open subset U sigma tilde. All the coordinates should be non-zero. So if we will have that some a row are positive, then it will vanish the corresponding coordinate, and it will be bad. So a row should be 0 for no, for the coordinates which are not in sigma. Да, потому что it is the affine space multiplied by the C star power something. Да. What is U sigma tilde? It is the affine space for the rays which are in sigma tilde, and it is C star for the coordinates which are not in this sigma. If они не нулевые. If we have some a row which is positive, then when t tends to 0, it will vanish the corresponding coordinate, and the limit will not belong to U sigma tilde. So all this stuff is in U sigma tilde. So the only coordinates which interplay are for the rays that are rays of sigma. Okay, so we obtain that a row are 0 for all row which are not in sigma 1. And now what remains? We have this condition, and if we write it once more, we have the sum for all the rays of sigma 1. We obtain a row, it will be 0. But we said that the cone is simplicial. So from this condition, we obtain that all a row should be 0, and the orbit of P is in fact in G0P, and it is closed in U sigma tilde. So it is closed in U sigma tilde, and the quotient will be geometric. Okay, I think I will
What do you mean
stop.
when you say the quotient is geometric?
Oh.
We also need to check when we throw out all this closed subsets, will be surjetic or not?
No. We have a very strange proof. Now I'm proving one statement. Suppose that the cone sigma is simplicial, then the map pi sigma from its preimage to u sigma is a geometric quotient. To prove this, I can use that pi is a good categorical quotient. So I know that pi is a good categorical quotient if I explain why each fiber is closed, then I get that the quotient is geometric.
Yes. Or okay, I think yes.
I repeat, we have a very strange plan to prove these two facts. First, we show that pi is a good categorical quotient. Second, we want to prove this. I proved one direction. I think next time I will prove in the other direction. If the quotient is geometric, then sigma is simplicial. And what is the final step? To show that maybe to show this and to show that the quotient is almost geometric. How do we explain this finally? We take a subfan of sigma tilde which contains only simplicial cones. It is an empty subfan. For example, we take the rays. If we take only the rays, it will already be a simplicial fan. If we know that the fan sigma is simplicial, then we just take it. If sigma is simplicial, then sigma tilde is also simplicial. Okay? No, sigma tilde is always simplicial. Okay, we take just the subfan. For simplicial cones here. And for the corresponding toric variety will differ from x sigma by some closed subvariety. And now the quotient will be geometric. If we glue up something, if we have an open covering such that at each affine set, the quotient is geometric. Then, all in total, our map will be a geometric quotient. So we show that for simplicial sigma, the quotient is geometric, and if sigma is not simplicial, then it is almost geometric. We throw out something, but on an open subset, it is still geometric. And we will be done. So it remains to show this.
I don't understand. We throw something from the large variety. But maybe when we also will throw out something from our factor of quotient.
No.
No?
What is G? G is a subgroup in this torus. It acts, each component, each C star, it acts on its own coordinate. We know that we have a toric variety, all in total. So if we throw out some G invariant subset, the remaining part will be also G invariant.
Yes.
So upstairs we have X sigma tilde, which is G invariant, so it splits into G orbits. If we throw out some G orbits, the remaining part is also split into G orbits. We have the orbit-cone correspondence. If we know that the T orbit is given by some vanishing, some coordinate hyperplane, then the splitting into G orbits will sit into the split into t orbits. I can repeat once more if you want.
But it can happen that when we throw out something from variety, then the map will not be surjective.
No, we say, suppose that at the very beginning we had another fan. At the very beginning we started with the simplicial fan. For this fan, maybe I didn't say that, our group G depends only on the rays of our fan. Do you remember on the previous lecture we said that this group G, which is the co-kernel of something, to construct this group G, we need only the rays of the fan. So we have sigma tilde and we have sigma tilde without something, but they have the same set of rays. So the group G is the same. So the splitting into G orbits is the same. The only thing which changes is, so since G is a subset of this torus, each torus orbit splits into G orbit. And we throw out some torus orbits. So the remaining part is split into G orbits. What about surjectivity? It will be surjective over the union of a simplicial cones.
Yes.
So for if we replace x sigma by another x, which is for the simplicial part of fan sigma, then the new map will be surjective.
Yes.
Just we make the same for the simplicial fan from the very beginning. And this suffices. We have a pi, which is constant on G orbits. To prove that it is almost geometric, it means that there is an open subset on which we have a geometric quotient. It doesn't map to the whole variety x sigma, but it maps to some open subset of x sigma.
So it's enough by definition.
Yes, it's enough.
Okay.
So the remaining part is to show this direction. Any other questions?
But then it's not correct to write it in such a way that x sigma is something quotient by G. Open subset in x sigma is something quotient by G.
Which quotient? This is?
Yes.
No, this is the categorical quotient. It says that the algebra of functions is in fact the invariant subalgebra. And this is true. This is we proved this at the very beginning. So the double slash is for the categorical quotient, and for geometric quotient we use the slash. Mm-hmm. Any other questions? Okay, then let's stop here. If you have any more questions, you can ask me later. Sorry? I think I can listen problems for those who go upstairs, then a very small break, and then we can have a seminar and discuss different kinds of quotients.
So we can submit problems now?
I think yes. Who can please stop the translation? Так.
Просто перевести, да?
Да, наверное, если можно. Сейчас.
Хорошо.
Спасибо.
Нет, оба раза от